We've seen the error analysis for the explicit Euler method, but we have not seen yet the error analysis for the implicit Euler method. In this video, we are going to do exactly that. And in fact, we embed this theory of error analysis for the implicit Euler method in a slightly larger framework. This will lead us to the notion of local discretization error. And this concept of local discretization error is extremely important in conducting the error analysis for a large class of numerical methods. Let's start with the definition. The local discretization error, also known as local truncation error, of a numerical method for a Cauchy problem is the error incurred after one time step when the initial value is exact. This local discretization error is important because, as we recall, these local discretization errors add up step by step. As we proceed with our numerical methods and perform additional time steps, the local discretization errors add up. So in the worst case, the total error that we have after a certain number of time steps can be bounded roughly in terms of the previous local discretization errors. So for that reason, understanding how these local discretization errors work, in particular understanding the local discretization error for a particular method, will allow us to immediately tell what is the global behavior of that method. If we know the error after one time step for a numerical method, then we also can tell the error after arbitrary many time steps. I need to admit that this definition is a bit shaky because we have not really defined what a numerical method is in general. We've seen a few examples, and I guess this definition gives you an idea of what we are talking about. But a more technically concise definition will be provided later in this class, when we have seen more examples of numerical methods. So as a warm-up, let's reconsider the error analysis for the explicit Euler method. So suppose we have got our Cauchy problem with a solution u, and we start at initial time t0 with some initial value u0. Then we can use the Taylor polynomial of first degree and the Taylor approximation theorem, which shows us that there exists a number xi. The xi is between t0 and t0 plus h, such that u at t0 plus h is the same as u of t0 plus h times u prime of t0 plus h squared over 2 times u prime prime of xi. That's a Taylor development for the function u around t0. And then we have got the iteration formula for the explicit Euler method. We already know u0, and u1 equals u0 plus h times f of t0 u0. That's just the definition of the explicit Euler method, where u0 is the initial value and u1 is an approximation of u at time t1, which is u at time t0 plus h. Okay, now let's compute the error. This is not very difficult. The local discretization error is just now the error incurred after one time step. We have the exact value at time t0, but at time t1, which is t0 plus h, we will have some approximation error. The approximation error is u at time t0 plus h minus u1. And to understand the approximation error a bit better, we plug in the first two formulas. So we see that u at time t0 plus h minus u1 equals u at time t0 minus u0 plus h times u prime of t0 minus h times f of t0 u0 plus h squared over 2 times u prime prime xi. We can simplify this considerably. First, we see, of course, that u of t0 and u0 are the same, just by assumption. This first difference, u of t0 minus u0, is equal to 0. Then in the next step, we see that u prime of t0 is just the same as f of t0 u at time t0, which, however, is completely the same as f of t0 u0. So this simplifies again, and So in the end, we just see that the local discretization error equals h squared over 2 times u prime prime psi. Okay, that's not difficult. But now let's work a bit towards the real deal to understand what the local discretization error is about. So this was the local discretization error after the very first time step. And now I'm going to explain what the local discretization error is supposed to be after the case time step. I believe these concepts are best explained with an example. We can basically proceed with the error estimate of the explicit Euler method. It's very similar to the previous slide. Namely, we do the Taylor series around tk plus 1 for the function u tilde. The Taylor approximation theorem tells us that u tilde at time tk plus 1 equals u tilde at time tk plus h times u tilde prime at time tk plus h squared over 2 times u tilde prime prime psi, where psi is in between tk and tk plus 1. And then again, we have got the definition of the explicit Euler method. So we have uk plus 1 is equal uk plus h times f of tk uk. So we can do the error analysis. The local discretization error is u tilde at time tk plus 1 minus uk plus 1. And just plugging in, we get u tilde at time tk plus 1 minus uk plus 1 plus h times u tilde prime at time tk minus h times f tk uk plus h over 2 u tilde prime prime xi. Again, we can do some simplifications. U tilde at time tk coincides with uk, so the first two terms cancel out. And furthermore, just by the definition of the differential equation, we have that u tilde prime at time tk equals f tk uk, so this simplifies again. And so the last term that remains is h squared over 2 times u tilde prime prime psi. So the local discretization error u tilde at time tk plus 1 minus uk plus 1 equals exactly h over 2 times u tilde prime prime psi for some psi between tk and tk plus 1. Okay, what is this good for? Well, typically we can obtain estimates for the second derivative of u tilde. For example, if f is differentiable, then we can derive an estimate on the magnitude of u tilde prime prime for all times, or at least for this short time interval from tk up to tk plus 1. And so to summarize, one can show that the magnitude of the difference u tilde tk plus 1 minus uk plus 1 is bounded from above by c times h squared, where c is some non-negative constant. In other words, the local discretization error of the explicit Euler method is bounded from above by a multiple of h squared. So as the step size h goes to 0, the local discretization error will also decrease quadratically. I believe it will be helpful to explain this with a picture. The green curve here is a graph of a function u, which solves a Cauchy problem. We have the initial value u at time t0 is equal u0, and the Cauchy problem has the differential equation u prime of t equal f of t u of t. Okay, that defines the green curve. And then this picture also shows the result of the explicit Euler method for a few time steps. We have got discrete time steps, t0, t1, t2, t3, and so on. And at each of those time steps, we compute an approximation of u at that time. So we start at u0, then we compute u1, u2, u3, u4, and so on. And as you might remember, u1 is an approximation of u at time t1, u2 is an approximation of u at time t2, and so on. And then what we're interested in is an estimate for this approximation error at each time step. For example, depicted here, you see this red arrow, which shows you the gap between u at time t6 and the approximation u6 produced by the explicit Euler method. Now, the point of the entire error analysis is getting an estimate for this gap between u6 and u at time t6. Now let me give you a drawing how this local discretization error fits into the picture. I define a function u tilde as a solution of an auxiliary problem, namely u tilde prime of t is equal f of t u tilde of t. So we just take the same differential equation as in the original Cauchy problem, but our initial condition is different. Namely, we start at time t5 and we say, okay, u tilde at time t5 is equal u5. In other words, we take the approximation u5 that has been produced by the explicit Euler method as a starting value for u tilde at time t5. Now what you see here, the dark green curve is the solution u tilde for one time step from the time interval that goes from t5 up to t6. And the local discretization error is the difference between u tilde at time t6 and u6. This is the local discretization error as we go from time t5 up to time t6. The local discretization error is the difference between u6 and u tilde at time t6. And I'm going to explain later how this will lead us to an error estimate that bounds the difference between u6 and u at time t6. All right, let's do the error analysis for the implicit Euler method. Our goal is to find an estimate for the local discretization error for the implicit Euler method, and that is a bit more complicated as for the explicit Euler method. In fact, it is a bit difficult to find the technical details for that in the literature. But nevertheless, we are going to do it now. The error analysis for the implicit Euler method requires a bit more assumptions. So let us from here assume that we have got some constant L that is non-negative, such that we have got our usual inequality. For all x and y that are real numbers, we have f of tk plus 1x minus f of tk plus 1y in Euclidean norm is bound from above by L times the Euclidean norm of x minus y. Let me remark that on this slide, on the next slide, I will focus on scalar valued ordinary differential equations. So u is just a function with values in the real numbers. The generalization to functions with that have values as vectors is only a minor modification, and presenting that would make it only unnecessarily difficult. So, equipped with that, suppose with our implicit Euler method we have produced approximations of the solution u of our Cauchy problem. So the approximation at time step tk is uk. And now we define our auxiliary problem. We let u tilde be the solution of the Cauchy problem u tilde prime of t equal f of t u tilde of t, with the initial condition u tilde at time tk equals uk. For the error analysis, we again use the Taylor approximation theorem. This time we develop u tilde around time tk plus 1 to get a formula for u tilde at time tk. So there exists xi in the time interval from tk up to tk plus 1, such that we have u tilde at time tk equals u tilde at time tk plus 1 minus h times u tilde tk plus 1 plus h squared over 2 times u tilde prime prime of xi. The minus in the second term, minus h u tilde tk plus 1, is due to the fact that we go back in time in this approximation. Okay, and now we substitute the ordinary differential equation, which u tilde satisfies. And so we can also write this as u tilde tk plus 1 minus h times f of tk plus 1 u tilde tk plus 1 plus h squared over 2 times u tilde prime prime of psi. And then on the other hand, we are dealing with the implicit Euler method. So we know that uk plus 1 equals uk plus h times f at time tk plus 1 uk plus 1. So we can start analyzing the local discretization error at time tk plus 1, which is uk plus 1 minus u tilde at time tk plus 1. On the one hand, we can substitute uk plus 1. So this can be rewritten as uk plus h times f tk plus 1 uk plus 1, and still minus u tilde at time tk plus 1. And next we insert the Taylor approximation, because we know uk is the same as u tilde at time tk. So we rewrite all this as u tilde at time tk plus 1 minus h times f at time tk plus 1 u tilde tk plus 1 plus h squared over 2 u tilde prime prime xi, and still plus h times f at tk plus 1 uk plus 1 minus u tilde at time tk plus 1. And we can do some simplifications again, and so the local discretization error can be rewritten as h times f of tk plus 1 u tilde tk plus 1 h times f tk plus 1 uk plus 1 minus f of tk plus 1 u tilde tk plus 1, and then still this additional term plus h squared over 2 u tilde prime prime xi. Okay, now let's take norms. And we also use the inequality that is satisfied by f. And so we get the Euclidean norm of uk plus 1 minus u tilde at time tk plus 1 is bounded from above by L times h times the Euclidean distance of uk plus 1 minus u tilde at time tk plus 1 plus h squared over 2 times the Euclidean norm of u tilde prime prime xi. Okay, the norm of the local discretization error is on both sides of this inequality. And if I let h be small enough, technically smaller than 1 over L, then I can pull over the term on the right-hand side, the norm of the discretization error on the right-hand side, and I can rearrange all this as follows, namely the Euclidean norm of uk plus 1 minus u tilde at time tk plus 1 is bounded from above by the inverse of 1 minus hl times h squared over 2 times the Euclidean norm of u tilde prime prime xi. Now if we pick h small, then we can bound the term 1 minus hl to the inverse from above. And typically with some conditions on f, we can also estimate the Euclidean norm of u tilde prime prime. And so again, we get that for some constant c, we have that the Euclidean norm of the local discretization error is bound from above by c times h squared. The same estimate as for the explicit Euler method. All right, let's return to this graphic in order to outline what we're going to do with the local discretization error. What we actually would like to have is an estimate for the global discretization error, which is the difference of u at time t6 and u6. In order to use the local discretization error to estimate the global discretization error, Let's suppose I already have got an estimate for the global discretization error at time t5. I can use that to get an estimate for the difference of u at time t6 and u tilde at time t6. As I recall, u and u tilde satisfy the same differential equation, but at t5 they have different values, of course. We can think of u and u tilde as Cauchy problems starting at t5, and only the initial values differ. We can use the stability theorem from our previous lectures then to estimate the difference of u at time t6 and u tilde at time t6. And now you can tell if I have got an estimate for the local discretization error and for this difference between u tilde and u at time t6, then I can use that to get an estimate for the global discretization error at the next time step. And we are going to use that technique in a proof by induction to get an explicit error estimate. What I'm essentially going to show is that if the local discretization errors are bounded by some power of h, the step size h, then I get an estimate of the global discretization errors by another power of h. Technically, it looks as follows. We have our usual assumption on the function f, namely, we suppose that there exists a non-negative L such that for all times t and all x and y, the Euclidean norm of ftx minus fty is bounded from above by L times the Euclidean norm of x minus y. Now suppose we've shown for the local discretization errors the following, namely that there exists a non-negative constant c such that for all the local discretization errors delta k at the time steps tk of our numerical methods, we have the estimate that the Euclidean norm of delta k is bounded from above by c times h to the p plus 1. If that is known, then the global discretization errors at time tk, which is ek, which is equal uk minus u at time tk, satisfy that the Euclidean norm of ek is bounded from above by the exponential of L times tk minus 1 times L to the minus 1 times c times h to the p. Now let me remark the following. As the time tk grows larger and larger, the error estimates get worse and worse, just as usual. On the other hand, as I decrease the step size, the errors converge to 0, and the higher the exponent p, the better. If for decreasing step size, the local discretization errors converge to 0 by order p plus 1, then I have something similar for the global discretization errors, and then the global discretization errors converge to 0 by the order p. So in that sense, I lose some power of h as I go from the local to the global discretization errors. So the better estimate I can derive for the local discretization errors, the higher the exponent p, the better the estimate I obtain for the global discretization errors. So let u be the solution to our Cauchy problem, u prime of t equal f of t u of t, with the initial condition u at time t naught is equal u naught. And furthermore, let u tilde be the solution to an auxiliary problem, namely the same differential equation, u tilde prime of t is equal f of t u tilde of t, with initial condition u at time tk equal uk. We wanted an upper bound for the Euclidean norm of uk plus 1 minus u at time tk plus 1. The Euclidean norm of the global discretization error at time step tk plus 1. Okay, the first thing we do is apply the triangle inequality. So we can bounce this from above by the Euclidean norm of uk plus 1 minus u tilde tk plus 1 plus the Euclidean norm of u tilde tk plus 1 minus u at time tk plus 1. I simply subtract u tilde of tk plus 1 and add u tilde of tk plus 1 and take the triangle inequality. Now the first term here is the local discretization error as we go from time step tk to tk plus 1. So we can bounce this from above by assumption by c times hp plus 1. And on the other hand, the last term, the difference of u tilde and u at time tk plus 1, can be bounded from above by our stability estimate. U and u tilde satisfies the same differential equation, only the initial values at time tk are different. So I can bounce this from above by the exponential of L times H times the Euclidean norm of u tilde at tk minus u at tk. Next, I realize that, of course, u tilde at time tk is just the same as uk. So in total, I get that the global discretization error at time step tk plus 1 is bounded from above by c times h to the p plus 1 plus exponential of LH times the Euclidean norm of ek, the global discretization error at time tk. Okay, now I can proceed with an induction proof. Let's first recall at time step t0, when k equals 0, we already have that the global discretization error is just 0. That's simply due to the fact that the numerical method and the Cauchy problem start with the same initial value, u0. Okay, now for the induction proof. That was our base case for the induction, and now we do the induction step. Suppose the theorem is true for some k, so we have this upper bound already proven for the global discretization error at the kth time step. So then we can use what we have just shown and get the inequality that ek plus 1 in Euclidean norm is bounded from above by c times hp plus 1 plus exponential of LH times the Euclidean norm of ek. That first line is just what we have shown. Using the induction assumption, I can replace the Euclidean norm of ek by the following, namely exponential of L times k times h minus 1 divided by L, and then times c times h to the p. We recall that k times h is just the difference tk minus t0. Okay, let's factor out 1 over L and h to the p. So I can rewrite this as L times h plus exponential of k plus 1 times h minus exponential of LH, and then multiplied with L to the inverse times c times h to the p. That's just some algebraic manipulation. Next, we recall that exponential of LH is greater equal 1 plus LH. So I can substitute that and get an upper bound. And then in the next step, I just cancel out plus LH and minus LH. So I get the upper bound exponential of L times k plus 1 times h minus 1, and then times L to the minus 1 times c times h to the p. And of course we see that k plus 1 times h is just the same as the difference of the time step tk plus 1 and t naught. And so I get precisely the estimates that I was looking for. In order to illustrate how that theorem is used, let's take a look at a few examples. Let's take a look at two examples, namely how this applies to the explicit and the implicit Euler method. So as usual, we have our assumption on the right-hand side f. Namely, we assume that there exists a positive constant L such that for all times t and all x and y, we have that the Euclidean norm of ftx minus fty is bounded from above by L times the Euclidean norm of x minus y, just as usual. For the explicit and the implicit Euler methods, we've seen that the local discretization errors satisfy an upper bound, namely they're bounded from above by some constant c times h to the square. In this case here, h has the second power. So if 2 is equal our p plus 1, then of course p is equal 1 in the formalism of the theorem. And applying the theorem gives us that the global discretization errors at time tk are bounded from above by the exponential of L times tk minus t naught minus 1 multiplied with L inverse times c times h. In that case here, h is just our h to the 1, which is just our h to the p, because p equal 1. The moral of the story is, the larger the exponent in the local discretization errors, in the upper bound for the local discretization errors, the larger the exponent is going to be in the upper bound for the global discretization errors. And in general, the larger the exponent, the better, because as I let h go to 0, as I decrease the step size, the local and the global discretization errors decrease faster and faster, the larger the exponent p. People have become quite creative in developing numerical methods for linear differential equations that have large exponents in the local discretization errors. It's no surprise that nothing comes for free, namely more complicated algorithms with higher exponents also incur larger computational costs, and typically they're also more complicated from a theoretical perspective. The explicit and the implicit Euler methods are just the most basic examples for several classes of numerical methods. And we're going to see a few of them in the future.